So what I'm going to talk about here is just a few of the key properties associated with transformation matrices that we need to know and work with. And then what I'm going to do is give you a few standard matrices that describe certain transformations which you should know and be aware of so that you can work with readily throughout any of the maths that we do at this level. So the first thing I want to highlight is about the inverse of transformation matrices. Now the effects of a transformation matrix can be reversed by pre-multiplying the position vector of the image by the inverse of the matrix associated with the transformation itself. So if we find the inverse of that and pre-multiply that point, essentially what we're going to do is reverse the transformation we're about to do. Yeah, so it's kind of like adding to then subtract, or multiplying to then divide. You know, you're reversing the process and getting rid of whatever you're doing to it. Now when the transformation is orthogonal, its transpose is equal to its inverse. So again, that's something that I'm just highlighting again that we should know from previous working material we've done on inverses. Second thing I want to highlight is about what's called invariant points. Now if we take a transformation on the point P, and if we transform that and then it is its own image, this is what's called invariant under the transformation, i.e. overall it doesn't actually vary. So let's imagine I give you the question, find all invariant points under the transformation associated with this matrix here, 2, 1, 2, 3. Now let's imagine we take a typical point, let's say x, y, and we're going to say that that's an invariant point. Now, the whole definition of this invariant point, what that means is if I take 2, 1, 2, 3, and I do the transformation on that point x, y, what I'll end up getting is the point x, y back again. I'll end up getting the column matrix of that point. So that is the definition of it. You do something to a point, you get the same point, essentially you've done nothing to it, despite trying to act a transformation upon it. So what we need to do with this is I will multiply through the matrix by this point. What I'll end up getting is 2x plus y, and I'll end up getting 2x plus 3y. And what I know is that that has to equal the original point itself, the xy. So what I can now do is equate the top and equate the bottoms, and I'll get 2x plus y equals x, and I'll get 2x plus 3y equals y. Now if I rearrange both of those, what I'll end up getting for the top one is x plus y equals 0, and the second one is 2x plus 2y equals 0. So essentially, this second one here is a multiple of the first. So if I were to take this first line here and just scale it up, I would get that second line. So what that means is that the system of equations has an infinite set of solutions, namely x plus y equals 0. So that means that all points on that line, or that curve x plus y equals 0, they're said to be invariant under the transformation. So that's how we look at calculating invariant points and equations of invariant points that are associated with certain transformations. The key thing is this first step here. You have to take a point that you're assuming is invariant, and then you know whatever transformation you enact upon that point will just get you the original point itself. There's actually no movement, no transformation, and no effects. Next thing is looking at what's called the transformation of loci. And essentially, what that's looking to do is answer the question, how do we calculate the equation of the image of a curve? Easiest way to do this is actually with an example. So let's imagine I want to find the image of the curve with equation y equals 3x squared under the transformation associated with the matrix A equal to 1, 2, 2, 3. Now, let's imagine what we're going to do is let the point AB be the image on the curve xy. Yeah, so the image of that point AB is on the curve x, y. Now we know the relation with A and B because what we know is that B is equal to 3a squared. Yeah, if AB is on our curve at some point, this has to be true. B equals 3a squared. But we then have to ask ourselves, what is the relationship between this and the point xy, i.e. the image of that curve? So what we know is that if we take our transformation matrix, 1, 2, 2, 3, and multiply it, and look to enact a transformation on any typical point on the curve, what that will give us is the image, which is what we assumed the xy is. So what we then do is we can take it and make this the subject. So remember, that's equal to a. So what that means is that this original point, AB, is given by the inverse of a times the xy. So essentially, what we're saying is if we multiply this point, we get the image. So going back the way to get the original point, we take the inverse matrix and multiply it by the image itself to invert it and basically get rid of the transformation that we've done. Now we know what a is up here. What we can do is then use that to calculate the inverse. So the inverse of a is equal to -1 over the determinant. Well, the determinant of this, is 1 over the determinant, but the determinant's -1, so we end up getting that. We then take the matrix and do the usual inversion. So swap the two corners there, 3 and 1, and then negate the signs on the other ones. So these are both 2, so they become -2. So we then know that the image AB, the point AB, is given by multiplying our image by this matrix here. Now it's -1 on the outside, so take that in, and what we'll actually end up with is -3, 2, 2, and 1. And that's then multiplying the x, y. So it should be a -1 there. So now that we do that, what we can then do is do the calculation. We get -3x plus 2y. We get 2x minus y. And what we know is that that then is equal to our point A and B. So if we take these, what I can say is fine. So A is equal to -3x plus 2y. And I know that B is equal to 2x minus y. Now we know from the fact that AB is a point on our curve, the relationship between A and B is given by B equals 3a squared. So what that then means is that if I substitute these new relationships for A and B in terms of x and y into this equation here, the B equals 3a squared, what I'll end up getting is 2x minus y equals 3 times 2y minus 3x squared. So what that means there is this is the equation of the transformed curve, but I've stated it implicitly. There's no way I can state it explicitly in y in terms of x or vice versa. So this is it implicitly stated, which is the transformed curve. In order to, we have to follow these sorts of steps. So find an arbitrary point. In this case, I've used A and B. X, Y, that would be the image of it. We then use this relationship here, the fact that the transformation times the point gives us that. Invert it and work back the way, and then we can state the equation of the transformed curve. The last thing I want to think about is composition of matrices, and that's really answering the question, how would we combine more than one transformation? So let's imagine I'm going to take a point, P, which is at AB, and I want to reflect it in the x-axis, and then in the line y equals x. So let's note the x, that's equal to 1, 0, 0, -1. What we're going to do is that's the matrix associated with reflection in the x-axis. So then the image of P given by xp, that's the equivalent of doing that transformation on our point AB. So let's refer to the transformation itself as big X. So what that then means is if I then look at taking the second transformation, which we said was the transformation in the line y equals x. Let's call the matrix associated with that transformation 0, 1, 1, 0. Let's call it L. Now that's the matrix associated with that transformation, so what we have to do is perform that transformation after we have performed the initial transformation of x. So what that then means is I want to essentially do L times x times p. So if I substitute in the matrices that I'm after for this, so that's equal to 0, 1, 1, 0 times the 1, 0, 0, negative 1, and then I've got my AB there. So if I do the matrix multiplication steps on this first transformation set here, so the two transformation matrices, what I'll end up getting is 0, negative 1, 1, 0, transforming my point AB. So this means that my composite matrix LX, which is the two transformation matrices composed together, that then is associated with this matrix here. So what we do is we obtain a matrix for the composite transformation by multiplying the two of them together, and then what we do is enact that transformation upon our original point. Now, one thing to note is the order of multiplication. Remember, the question that I asked was, I first want to reflect it in the x-axis, then in the line y equals x. So my order of multiplication is important. This is my second transformation, this is my first. We have to do it in that order. If I did it the other way round, what would be happening is that I'd actually end up with a different transformation matrix associated with the composite of the two transformations, and that would give me a totally different solution from the one that I'm after. So remember that order of multiplication information there. So a couple of the key things that we need to know and work with when it comes to matrices and their transformations. A couple of key properties that we're looking at. Now, I mentioned at the start there are a few fundamental transformation matrices we need to be aware of. So these are some that you really need to make sure that you've kind of got in the back of your head and that you remember what they are and the transformation associated with them. So there's 8 big ones. First matrix here is the anticlockwise rotation about the origin through an angle theta. The second one there is the clockwise rotation about the origin through the angle theta. So this first matrix here, let's imagine we're looking at that. So we've got our bit there. There's our transformation theta in the anti-clockwise direction. So that's this first one here. If I was to go clockwise and go down this way, so let's say that is there represents my transformation. There's my angle theta. That would be what the second matrix represents. This one here, this is the matrix associated with the transformation by reflection in the x-axis. And this is the one associated with reflection in the y-axis. Fairly similar, it's just a sign that's reversed. The next two are associated with reflection in the line y equals x and y equals negative x. This would be the reflection in the y equals x. And as you'd imagine, for the line y equals negative x, we've negated the x. So we're just negating the terms, i.e. instead of 0, 1, 1, 0, it's 0, negative 1, negative 1, 0. We've then got our matrix here associated with reflection in the origin. So that's given by negative 1, 0, 0, negative 1. And then finally, our matrix where we scale up or scale down, so we look at dilation or reduction, is given by k, 0, 0, k. Now, for this one, if k is bigger than 1, this is dilation. So this is expansion, this is scaling up. If k is less than 1, this is reduction. So this is us making our line smaller, or our image smaller for the points. These 8 matrices here, these are kind of standard matrices you should remember. We need to be able to work with these ones openly and recall them fairly quickly, such that we're able to work through our questions at a relatively good pace and understand what each of these transformations refers to when we see the matrix itself working in questions. Remember all 8 of these if you can. They're very important and vital to some of the work that you do when it comes to working with matrices.